our next speech comes from Soundplus, a director of product marketing, Mr. Jingpeng. So Jingpeng, please welcome Jingpeng to give the speech, and I give the floor to you. Thank you, Jingpeng.
Okay, thanks, Alex. Hello, everyone. My name is Xiang, and from Soundplus. Today, I'm honored to be able to share my insight about speech enhancement on true wireless earphone, that is TWS earphone, with you through the tinyML Asia. In Soundplus, our team have rich experience in audio algorithm and embedded software development, focusing on provide end-to-end audio and voice enhancement solution to consumer electronic products. We're fortunate to work with the senior algorithm scientists, engineers, and product manager in the industry to create better audio consumer electronic product for the consumers. The audio features set can be roughly divided into 4 areas: voice pickup for calls, active noise cancellations for the control of ambient sound, as entrance of the voice interaction and headset original function for sound playback. True wireless headphones have been quickly become one of the optimal solutions for hands-free calling due to their ease to wear. Besides picking up a phone call, the popularity of telecommunicating, online education, and emerging scenarios such as live streaming and UGC, that user-generated content, this emerging usage of TWS headset have raised extremely high challenge for headset sound pickup performance in diverse acoustic environment. On the other hand, the popularity of in-ear headphones have dominated the market over the past 3 years with the active noise control, that is ANC features. The headset can adjust the ambient sound that users hears. Hybrid ANC headphones use the feed-forward microphones and feedback microphone as input to the controller, and feedback microphones located inside the headset towards the ear canal, and therefore becoming popular. As a personal device, TWS headset can be seen as an entrance to the voice interaction. But of course, it's facing more complex use scenarios than those smart speakers, as well as extremely limited computing resources and power consumption limitation. Finally, the core function of the headphones is the sound playback. It will continue to move toward a more excellent listening experience, more personalized and intelligent. Those audio features bring many technical challenges behind the benefit of the TWS headset. For voice capture on TWS devices, there are 4 challenges that need to be dealt with. First is high transmission loss, especially for a high frequency component in the voice. The earphone equipped with a microphone located at the back of the mouth with an angle. However, when a person speaks, the sound wave radiates to the front, which means that using the earphone's microphone to pick up the voice is not as effective as the phone does. And the microphone pairing on the small ID, when the aperture of the microphone array is less than 30 millimeters, the performance of the beamforming is more likely to be affected by microphone mismatching. The key is to have a paired microphone response and a sufficient isolation between the 2 channels. However, this means higher cost for hardware design and manufacture. The space on TWS headset is limited, so the battery is limited as well. low power consumption means few computational resources, while high noise reduction performance is required in those complex acoustic scenarios. In the wind noise and the strong interference, the turbulent pressure interference from wind cause high-level noise on microphone that may saturate the microphone diaphragm, causing their sensors information to be corrupted. With this would affect both ANC application and the speech enhancement application. To address the challenge of the voice enhancement on TLBAS headset, Soundplus voice enhancement, that is SVE solutions, is categorized by the number of sensors used to pick up sound, starting with SVE-1000 series, which use only one microphone. The deep neural networks have the ability of nonlinear modeling and a good discriminative performance for dynamic noise interference. In our solution, both magnitude and phase information are modeled in the network. By doing so, the AI speech enhancement model effectively improved the speech quality of TLBAS headphones in those dynamic interference environments, achieving excellent SMOS scores in objective test and receive positive feedback in subjective test. The SVE-1000 solution support the real-time application, which means that it control the system delay within several milliseconds. Specifically, it's 16 milliseconds for the frame length. And the benefit of using only one microphone on the TLBAS headset is that it's very compatible with the ID design and have a rather low requirement for the manufacturer phase. But the single-channel solutions is limited by the resources of the computing platform. When the signal-to-noise ratio, that is ISNR, is below 3 dB or even negative in a radio noise condition, the stability of the neural network model will be reduced. Also, using only one microphone means the microphone is vulnerable to the wind noise saturation. The SVE-2000 series combines the adaptive beamforming and the machine learning method, becoming more adaptive but adaptable to the noise environment, achieving higher noise reduction performance. Meanwhile, because the beamforming can specially filter out the surrounding interference, the ISNR of the input signal of the neural network is therefore improved, so the small resource model can also work stably in the challenging environment. Using the deep learning method, we can more accurately identify speech component from noise component and complement higher frequency harmonics to make speech sound fuller and clearer in the noise environment. This is the pipeline of the SVE-2000 5X series. The dual mic array is acting like a adaptive beamformer, and also used to estimate the wind noise level in the environment. These two blocks have an interactive information change with the deep neural network, and the deep neural network can therefore have some feedback for the beamformer, making the beamforming working more stable in the with dynamic interference. Another combinations of two microphones is using the feed-forward and feedback mic in hybrid ANC applications. The SVE-215X series reuse the combination of two microphones to capture users' own voice. The feedback mic picks up the low-frequency component of users' own voice in the ear canal, which can provide better quality low-frequency voice information in particularly noisy environment, such as in high-speed wind. Using the feedback microphone signal in speech enhancement have two problems. First, the voice signal received by the feedback microphone, which receive the influence of change in wearing conditions, has a large dynamic range. The neural network models guide the mixer to ensure that call quality is maintained as much as possible under different wearing conditions. Our solution includes a highly dynamic echo canceller too, to cope with the large echoes received by the feedback mic. And the neural network model is trained to take into account the large dynamic range that exists in the inner and outer ear signals. The second problem using a feedback microphone to capture user's voice is when the ANC function is turned on. The signal received by feedback microphone will change because the feedback ANC is turning on. Especially when it's windy, it's easy to receive wind noise from the feedward pass, so that the voice quality will be degraded too. Therefore, a wind noise multi-level detection and control of the ANC pass is required. To address the impact of the wind noise on ANC and the ENC applications, we use two microphone combinations. The first is using an external dual microphone array which consisted of feed-forward mic and talk mic, or using a combination of feed-forward and feedback microphones to do the multi-level detection of the wind noise levels from the breeze that doesn't require any process to the audible wind speed level that need to control the ANC controllers. The modified ANC parameters balance the noise heard by the users in windy scenarios, and the ambient noise are present at the same time levels, optimizing wind noise, hearing, and preserving ANC performance in the main frequency band with a given headset structure. With these precise estimations and regulation of wind noise from the feed-forward pass, the turbulence noise at feedback mic is therefore limited, ensuring the quality of the call in windy conditions. Though there is always some analyze process going on when the earphone is weared, so the wind environment analyze and the wind noise estimators are scanning the environment using the combination of the microphones. Once the estimators detect the wind interference, it will therefore control the ANC feed-forward controllers and feedback controllers to provide a balance between the wind noise and ambient noise that users finally hear. When a TWS headset has both beamforming microarray and then hybrid ANC functions, the SVE-3000 series fused deep neural network with adaptive beamforming and voice information from in-ear microphones. In the most scenarios, the ISNR is above 6 decibels. This algorithm leverages DNN to enhance the performance of beamforming as well as SVE-2000 does. In very noisy conditions, like busy roadside or in the strong wind, the neural network is also used as an adaptive mixer that uses feedback mic to capture users' low-frequency voice component. So the 3000 series basically combine the benefit of the microphone array and the in-ear microphones to provide as good as possible good qualities in most user scenarios and keep the voice intelligent when the wind or the outside interference is really strong. On the top of the 3 microphone systems, voice pickup unit, that is VPU, can further improve the voice qualities. The VPU is especially designed for picking up band conduction voice signals, which is more stable for different varying conditions compared to feedback microphone. And the phase information of this signal is closer to air conduction microphones. Another outstanding advantage is that VPU has low sensitivity to noise and echo from air conduction paths. SVE-4000 series merge multi-channel signals from VPU, feedback mic, and adaptive beamformer. Using this deep neural network model to adaptively compensate the dynamic difference in the voice signal under different varying conditions. So the SVE-4351 solutions leverage this nonlinear modeling advantage of deep neural network to enhance beamforming, to enhance performance of beamforming, and also attenuate those dynamic noise, and also some residue echoes from the echo cancellations. And these solutions support windproof features, more than 18 mile per hour wind directly blow on the inlet of the outside microphones, and provide a clear and authentic voice. Another solution using a 4 microphone as array is for overhead headphones. Those SVE-4005X is designed for this full cup headphones, which have a total 4 microphones for voice pickup. Using a 4 microphone on the left and right side of the headset to form multiple arrays. This algorithm combines the adaptive beamforming with deep neural network model to provide natural and clear voice and stable high noise reduction performance. In the test in the metro, the noise in the carriage is about like 90 decibels, and the call quality can be comparable to the effect of answering using your mobile phone in a quiet office. This is done because the deep neural network further enhanced the performance of this multi-adaptive beamformings, and especially in those dynamic noise interference. Through the above introduction, we can see that behind the co-function on the headset nowadays, it involves several complex algorithm models working together. But the headset is always very tight in terms of computing resources and battery power due to its limited size. The SVE-AI solutions, which incorporate machine learning method, is designed to take into account the computing power and the memory specification that the chipset can provide. And each algorithm module remains flexible and can be configured separately to fit each positioning of the product. I think
may I
yes.
have a quick question? So we receive questions from the audience. Do you want to prefer to answer now, or you want to answer after the finish of your speech?
I see the question is about the samples of the persist speech. Yes, later there was a slide to show the persist speech and raw microphone signals.
Great, thank you.
Okay.
Yeah.
So
thank you.
Our deep neural network, the training to continue to introduce our deep neural network. First of all, the training of the networks is carried out with 8-bit precisions from the beginning. So all the calculations involved are performed in a fixed point. So the network parameters can be divided into 4 levels from level 0 to level 3, according to the number of the network parameters from small to large. And the smallest network, L0 are less than 40 kilobyte. Taking the chip with ARM Cortex-M4 float instruction as an example, the SVE-2051 level 0 uses less than 150 kilobytes of RAM, and computation consumes less than 80 millicycle per second, that is MCPS, on a single M4 float core. And the SVE-3151 L1, which combines a dual microphone array, the feedback microphones, and a small neural network unit, also use no more than 200 kilobytes of RAM and the computational complexity of less than 120 MCPS on a single core. If the chipset provides more memory resources, the SVE-AI solutions supported the rapid replacement of the neural network models that is used, maybe with a larger parameter set, thereby improving the noise element reduction performance and have a better voice performance, like a higher SMOS. And
yeah.
Yep.
Jingpeng, there is another question coming up that can DNN speech enhancement lower the energy cost compared with the traditional speech processing algorithms?
Okay, I got this idea, but however, in the industry, the traditional speech processing, let's focus on the true wireless headset, because it's rather like a near-field applications to those very complex traditional speech processing, like de-reverberation or multi-microphone arrays processings, are not it's not used on the TBAS headset. So the traditional speech processing used in TBAS headset is rather like using a few MIPS on the chipset. So the using of the DNN is not to lower the energy cost, but to enhance the performance of the noise reduction performance.
Okay. Thank you.
Yeah.
Thank you.
Okay, so let's move forward to analyze the SVE-AI solutions compatibility with the system on chip from the perspective of power consumption. When an ARM Cortex-M33 architecture CPU runs at 100 MHz, the additional power consumption brought by the algorithm is less than 4 milliwatts. During the phone call, the CPU clock boosts from about 50 MHz to 100 MHz. Used to support SVE-AI calculations, the algorithm brings about 10 milliwatts in addition to the power consumption, which is the typical current level of TWS headset. In particular, the algorithm currently contains a multi-layer neural network interference. Most of the calculation is performs with 8-bit format data, vector and matrix operations. If the chip have the corresponding acceleration instructions, the neural network part of the calculation can be accelerated by several times or even several 10 times, thus further reducing the power consumption level. This part we're also working with ARM to verify the actual acceleration performance of the next generation Cortex-M55 and Ethos U55 instruction set for our algorithm. The SVE solutions also include some always-on functions that run continuously on the devices, which involve computation that work at extremely low power levels. For example, the wind noise detection based on dual microphone combinations, and an intelligent ANC function that run in the sensor hub of the M series architectures consumes less than 10 MCPS of computations and can work at the lowest main frequency of the chip. Another function that has been running continuously on the devices is the voice recognition on the device side. The KWS function includes buffering the microphone data, the voice activity detections, and beamformer for noise reduction in a noisy environment, and finally the keyword decoding. According to the regular use frequency of 10 callback in an hour, this solution is increasing the average power consumption within 1 milliamps, causing no significant reductions in the standby time. Here is the sum up of the SVE series and its mass production showcase. For those headsets that carry only one microphone, the use of the deep neural network method brings it with dynamic noise reduction features. The noise product from Oppo, One More, and Audio Technical, another brand, are using our SVE-1000 series. So that's SVE-2151 using the combination of feed-forward and feedback microphone to capture user's voice even in the windy conditions. It's compatible with any earphone that support hybrid ANC. The SVE-205 series fused the advantage of neural network in dynamic noise reductions and the special filtering effect of adaptive beamforming, providing authentic voice when SNR is above 6 decibels. This solution also used to enhance keyword spotting for performance in the noisy scenarios. For those headsets designed for business call and call center usage, the SVE-2051 L1 and L2 models support a mainstream certification standard such as Teams 4, or Zooms. With the popularity of ANC features on TWS headset, is using both two microphone arrays and feedback microphones to capture using user's own voice. With the addition of the neural network, the microphone array algorithm works more stably under dynamic interference, providing a natural linear output in the most scenarios, which can be also used for communications as well as helping speech recognition applications. And the addition of the in-ear microphone make it impossible to ensure speech intelligibilities even in extreme scenarios. The SVE-4351 supported the VPU to provide even clearer voice in active SNR conditions. You can see the most of the mainstream audio or mobile phone brand TWS headset are using our solutions. And the SVE-4000 series also been adopted by JBL Tour 1, which is launched in Europe this year, providing excellent voice enhancement. That is a comparison between the raw microphone data and the processed data by SVE-4050. If we can hear the raw microphone signal.
Yeah.
So you can hear the bubble noise in the background and some clips from the dish and the glass. Hear the output.
Mm.
4 hours of steady work fates us. A young child should not suffer fright.
And see the voice from the users is kept intact while the dynamic interference eliminated. It's all running on a knob-based M series chipset.
Jingpeng, while we are here, there is also a new question for KWS in noisy conditions. Is the dynamic noise reduction the only noise oriented method you are applying?
For those headset using keyword spotting solution from Soundplus, our neural network is adapted to our like the adaptive beamforming process. So the dynamic noise reduction. So our keyword spotting solutions using both the beamformer and the neural network to keep the spot rate high in the noisy conditions. But if the device is connected to the cloud or uploading some stream or the PCM to the cloud for further ASR or NLP applications, because our front end processing may not compatible with especially the neural network with such limited resources, may affect the performance of the cloud applications. So in that scenario, we only use those special filtering from the adaptive beamformer to enhance the performance. However, as I introduced, if the SNR is not that extreme, like a negative SNR, our neural network can also be used to enhance the performance of the beamforming. So the output finally be uploaded to the cloud is still the output from the beamformer. However, the beamformer can work more stable with the help of the neural network.
Mm-hmm. Okay, thank you. And yeah, if there's additional question, please feel free to put a question on the question box. Please go ahead. Thank you.
Okay. The next page, I'll introduce our middle to long-term roadmap. So in the Soundplus, we are focused in the application of audio algorithm, both in voice enhancement and some active enhancement, like ANC involved. So from this four field, at the bottom is the voice enhancement applications. So further merged multiple sensors fused by the AI method to provide a stable and then compensate for the personal dynamic range from the wearing conditions or to the different sensors specification. And in the next year, we'll put more time into the bandwidth expansion of those in-ear transducers, because the conduction path from the bond conduction, only low frequency component can be heard by those in-ear transducers. So using AI method to expand the bandwidth of those sensors become important in the solutions. For those active, please go ahead.
Yeah, so while you are talking about the sensors, there is a question related to that. What kind of microphones you recommended, MEMS or ECM for your algorithms?
Okay. So the MEMS microphone have two advantage over the ECM on the TWS headset. The first is that have a smaller size. Take a feedback microphone as example. The space in the earphone is very limited. So it's the most common size is 2.7 and 1.8 millimeters by length and width of the microphones. The second advantage, but also very important of the MEMS microphones, because it have a rather good pairing within the same batch of the microphones, and you pick up like two from the two microphones from this batch. It's possible have a very good matching between them, like within the 3 decibels frequency range, or like 10 degrees of phase response in our interest in the frequency band where we're focusing. Like mostly we need the microphone to be pairing between 50 hertz to 10,000 hertz, which is most the voice component located.
A follow-up, another question is, can the algorithm detect heart rate monitoring using the MEMS microphone with a low-pass filter for in-ear designs of the blood flow? Okay.
That is a question related to the healthcare on the IoT devices, and my answer is yes, because the heart rate can be detected for a long time using the headphones. The first application I remember is using a lower headphone to detect the heart rate, because you can detect this very strong low frequency pulse repeat one by one using the microphones, but however, it face some challenging in the real applications. The first is the SNR might be very low when the user is like running or taking in the commute, because the noise is rather high than when you in indoor. So the detection may be not that precise enough to provide any healthcare informations. But yes, if you want to try using a microphone, in-ear microphone, to detect the heart rate, you can find that pulse, especially if there's some space for this pulse to resonate in the ear cup. For the insert earphones, I currently don't have some data to support my suspicions, but I think yes, if you don't filter out those low frequencies signals from the feedback microphone, you can find the heartbeat from the streaming.
Great, thank you. Thank you.
Okay, so for the active enhancement applications, we are currently working on the open type ANC for those like AirPods 3, the type of the earphone do not have silicon tubes, and then this application required an auto fitting of the personal user's ears, and then an auto leak controls to compensate the low frequency output of the speakers. And then when these features are integrated to form the SVE-3000 series, we will provide a personal ANC mode for both open type earphones and insert type earphones. which include an ear canal calibrations to provide a personal EQ to provide a uniform listening experience on different users' ears. And further, we hope to see those chipset with equipment with high frequency or high clock running FIR filters, so the hybrid ANC controllers can be merged with adaptive ANC algorithm using both IR filters and FIR filters to provide even better ANC performance on the TBAS headset. And for those the voice user interface applications, now we're putting effort to develop an ultra low power voice UI based on those feedback microphones or VPU that hear the voice from the user's ear canal, that can solve the problem of low performance or poor performance in the windy scenario for those voice applications. And also, because of the concern of the privacy, the consumers are needing a mini ASR applications based on those feedback microphone or VPU. For the healthcare applications, we're now more focused on the enhanced experience in transparent mode rather than like hearing aid applications, because we find the wind noise still a huge problem in the transparent mode, as well as the user's own voice being amplified with ambient sound when the user is turning on the transparent mode. So we're using a different method, and including a beamformer and a neural network to solve those questions in the transparent mode. And further, if the anti-holding and the dynamic range controls is used, users can further enhance the ambient sound, forming those augment hearing features on the TBAS. That would require multi algorithm working spontaneously, especially this low latency speech enhancement in the noisy environment. That would require higher computation consumptions and more interference per second.
Yeah. Jingpeng, while you are here, there is another question from Mr. Hasanali, that what are the current challenges for adopting IIR filters for ANC instead of the traditional FIR, besides the stability concerns? And also please confirm the previous question of the MEMS or ECM are answered.
Yes, we would recommend MEMS microphone on the TBAS headset over ECM.
Okay.
Yeah, and for why we're using or the industry using those IR filters instead of more stable FIR filters, because of the power consumption on the headset is very limited, and then the small IDs means the latency between the error microphones to the controllers is very small. Normally, the mainstream ANC chipset need to finish this filter performance within 10 how to say that 10 how to say
millisecond?
Not millisecond, the 1000 millisecond, the
micro.
The millisecond, right?
Microsecond, right?
Let's see this.
微秒是吧？
对，
micro.
Microsecond. Microsecond. Yeah. It's like 10 microseconds. So if you are using a like 512 tapes FIR filtering within 10 microseconds, it's like 500 MIPS on the on an ARM SoCs. So that would be too much power consumption on the headset. So industry adopting now, they're adopting the IIR, which may be like 10 or 16 tapes, cascaded bicode filters to save the to save the power consumptions.
Okay, great, thank you. Another question is that do you think Soundplus technology can be applied if a sensor is strapped into an antenna, the front of the chest, above the heart, using MEMS microphones and AI algorithm for HRM detection with the noise cancellation?
This question is basically focusing on using a MEMS microphone to detect the heart rate with noise cancellation. Yes, I think with with enough experience data and maybe need addition of data with some common users scenarios, we can find a way to filter out those noise at the low frequencies using both traditional method combine it with some neural network ways to detect the heart rate detections. But I think it depends on what purpose of these heart rate detections is, just for heart rate calculations or for some healthcare monitor, because the noise cancellations processing may further compromise some healthcare info from your heartbeat.
Yeah, it's more for sports heart rate monitoring.
Okay, I think it would be more easy to integrate into the sensor hub of TIDBAS using the feedback microphone in the ear canal. So you'll see more and more TIDBAS headset have a heart rate monitors features in the future. Okay. Yeah.
Great. Thank you. Okay. Jingpeng, one more question. If the answer stressed on the benefit of IIR filters, but how come they are not adopted earlier? If so, i.e. so far FIR filters have been used in implementing ANC?
Okay, I see the questions. Yes, take a vehicle ANC as example. It is using FIR filters on the controllers, and they have multiple feed-forward microphones and then the arrow microphones nearby the ears. But in for the headset applications, your feed-forward microphone and the distance between your feed-forward microphone and the arrow microphones mostly is just 1 centimeters or like several millimeters. But the sound travels rather fast in the air, so the latency is getting very small, as like 10 milliseconds. So all the FIR calculations on the digital domains need to be finished within such small time. That means rather high MIPS consumed by the chips, and because FIR is the frequency calculations, you cannot parallel accelerate the processing with parallel structures like a neural network. So if you want to apply FIR filters on the TIDBAS headset, that need hard work on the chipset side, and maybe yes, in the research in the industry, different teams are trying to use like neural network to predict the noise in the next frame or in the futures, in the very short futures, to compensate this latency problem. But the difference between the headset ANC and the other ASIC applications is the small latency on the earphones.
Mm-hmm. Okay, thank you.
Okay, that'll be all of my content to share today. Thank you.
Okay, great. Thank you, Jingpeng, for the great speech, and also thanks for the good questions from the audience. That is a very interactive session, and thanks again, Jingpeng, and looking forward to future collaboration of your company with the audience and with the partner companies as well.
We want to thank especially our strategic partners who have made it possible. We have our executive sponsors, ARM, the Software and Hardware Foundation for tinyML, then at Impulse tinyML for all developers, Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous, Sentient end-to-end deep learning solutions for tinyML and Edge AI, then platinum sponsors, Reality AI, add advanced sensing to your product with Edge AI, tinyML, and then Renaissance, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge, Maxim Integrated, enabling edge intelligence, Seed Studio, the IoT hardware enabler, SensiML, build smart IoT sensor devices from data, SynSense, build sensing and inference hardware for ultra-low power embedded mobile and edge devices. And our silver sponsors, Aeon Devices, Deep Light, EMSA Visual Sense, Greenwaves Technologies, Gravity Inc., HODG, Imagimob, Kixo, Rixen Technology, and SAP. So thank you everyone for staying with us today, and see you tomorrow.